All right, YouTube, welcome back. Today we're going to take a look at a C13963. This is a high driver board or high current driver board out of a Williams Funhouse pinball. This board drives Rudy the Clown, who's in Funhouse, his potty mouth. This is the board that drives the motor that makes Rudy's mouth open and close. We're looking at this board today because the owner has said that the output voltage on this board is kind of low, and he's gone through a couple of motors and he's a little concerned. So we're gonna take a look at this board, see what we can do to sort of help out a bit and make sure it's working properly. Talk about it and its related products, things, related games, other places it's used, and generally everything there is to know about this board so that you can keep Rudy's potty mouth going. So let's dive into it. Alright, so the first time this board was used in a pinball game was in Funhouse. As we said, to drive Rudy's mouth up and down. And this is called by Williams a high driver board or a high current driver board, depending upon which particular page of the documentation you're looking at. And the way this board works is that on the J1 connector over here, it has 4 pins, you can see. 2 of these pins, there's a 12 volt, the top pin is 12 volt, and then the one below it is ground. And this is the input to the board. This comes from the unregulated 12 volts in a WPC, off the WPC driver board. And then the bottom 2 pins are the very bottom pin here, pin 1, enables the voltage on this board, enables the output voltage. And then the pin above that determines the direction the motor spins. And we're going to take a look at these a little bit later when we have this board on the bench and we're testing it out. The output that this board, even though it has 3 pins, one is a key pin, really only this top pin here and this pin right below it, these are the outputs that actually go to the motor. So that's all it is. This board is, as I said, a C13963, was first used in Funhouse. And this board drives a motor, which is a 12 volt motor, which is part number A13997. Now that same motor is actually used in Red and Ted's Roadshow to drive the mouth for Red and Ted. And what's interesting, however, is that this board is not used. Williams decided not to do 2 of these boards in Roadshow, but instead created a single, what they call dual H motor controller board, where they have one board, which is essentially like taking 2 of these boards and putting it together into one board. I'm not entirely sure why they did that. It would just have been easier just to stack these 2 boards, and then for troubleshooting purposes too, you could have swapped boards and it would have been easier, but instead they decided to like engineer another board entirely. Who knows why? We'll look at that in a second. But this motor control board was also used later on in NBA Fastbreak for the Defender motor. And if we take a look here, this is the board from an NBA Fastbreak. It's a picture of a board, actually. It's not the board itself. And it goes by a couple of different part numbers. One is the A21568, which is the board with the bracket riveted to the board to mount underneath the playfield. You see the Roadshow board, the Funhouse board doesn't have the bracket. Instead, it has these plastic standoffs that screw underneath the playfield and hold it on. This one just has 2 screws, and this board hangs vertically underneath the playfield, whereas this board screws up underneath the playfield in Funhouse. So that's the part number for this board with the bracket. The board itself, the part number is almost the same as Funhouse. It's a C13963-1. And the reason for the -1 is that there's one big difference between the board in NBA Fastbreak and the board in Funhouse. And if I put these right here and zoom in, you'll actually see what it is. And it's basically this resistor here. This resistor is on the Funhouse board, and here you see what Williams did was they removed the resistor, and instead this is a 0 ohm jumper. So instead of running the voltage through this resistor, there is this 0 ohm jumper here, and we're going to talk about that and what that means in another second. But other than that, these boards are interchangeable, and in fact it could be argued that the -1 board is even better for Funhouse, and we're going to talk about that in a moment. This is the board layout parts description for this board, and just like most Williams documentation, this has an error in it, and you should be aware of the error, and it specifically has to do with R9, which is this big resistor that's on the board. And the parts listing in the manual, you'll see if I can zoom in here, you'll see it actually says that the resistor is 5.6 k ohms at 5 watts 10%. Well, guess what? This is not a 5.6 k ohm resistor. As you can see here, this is a 5.6 ohm resistor. If you put a 5.6 k ohm resistor in here, you're basically, this board is not going to work. So when you're looking at this board, don't get fooled by this parts description, and just go by what you see on the board, especially if the board's never been touched before. This is more likely correct than what you're going to see in the parts description. So I just wanted to highlight that, because obviously somebody in the Williams documentation department made a mistake, and they should probably be fired. Oh, I guess that ain't going to happen. So if we look at the schematic for this board, you'll see that it has the input over here that we talked about, and you have your 12 volts, your ground, your key pin, your driver up and down, and then your enable. And that's these 5 pins over here that you see on the board right here. Okay. Then you have an LM339 that's sitting here, which is responsible for telling the output of the board which direction to go in. Because it's a DC motor, it's a 12 volt motor, you have either positive or negative, and depending upon whether the driver up down is enabled, you'll either have the current flowing in one direction here, which will spin the motor one way, or you'll have it flowing in the other direction, which will spin the motor the other way. And that is determined by what happens with pin 2, which is the driver up down, which you can see here is controlled by solenoid 22 on the driver board. And basically what the computer would do to determine which direction Rudy's mouth would go in is it will either turn this solenoid on or off, and when it turns it on, what it does is actually grounding this pin, putting this pin to ground, and that will change direction. So when this pin is not grounded, it will go in one direction, and when it is grounded, it will go in the other direction. Now, the other interesting thing to note is the enable line here. The enable line is what actually turns the motor on or off. and that's solenoid 21. And just like solenoid 22, to turn the motor on or off, the computer turns it on and it grounds this pin. And once this pin is grounded, you'll see the motor will turn on. So as long as this pin is not grounded, you won't get this motor turning on or off. And once this pin is grounded, this motor will turn on. It will go in one direction, and then if solenoid 22 is turned on and the driver up down is grounded, then the motor will spin in the other direction. So the interesting thing about this board is that it uses what's called complementary transistors. And you see here the complementary transistors are a tip 102 here and a tip 107 here. And complementary transistors create what's called a complementary symmetry, or sometimes called a circuit, or sometimes called a Class B amplifier. And the Class B amplifier, it allows the amplifier to drive the power through the load in both directions at the same power. So if the power is going in one direction, these two transistors are responsible for driving it, and if the power is going in the other direction, these two transistors down here are responsible for driving it. And so what this does is it keeps the load shared evenly, and allows for the high power to keep that motor spinning, because that motor has to spin pretty fast in order to keep the jaw moving on Rudy or Red or Ted or whatever. And that's the reason why these tip 102s and tip 107s are utilized. In fact, if you look at the data sheet, if you look up data sheet, if you Google tip 107 data sheet, you'll see it's a data sheet that has both a tip 102 and tip 107 on it, and vice versa. The last thing here is there's an additional tip 107 that's used, and this is to enable this whole circuit to work. Now, the other interesting thing I just wanted to point out real quick is what the circuit looks like in the dual motor board for Red and Ted. And in fact, this is over here, this schematic is just for this board and drives one motor. If you see here on the schematic for Red and Ted and the dual H motor controller board, you'll see that there's motor 1 here and motor 2 here. And if I were to draw a box basically around motor 1, let's say, and if I were to compare what's in this box with this schematic here, you would see that it's pretty much the same thing. So it's very basic electronics. Class B amplifiers are one of the things that are very common in electronics for building power amplification circuits. And Williams used very sound, very basic engineering here. But like I said, why they decided to create a whole separate board, here's what the board looks like, the layout for the board looks like, the dual controller board, as opposed to using just 2 of these boards. I don't know. That just seems honestly like a waste of money. And more parts, but who knows? Maybe they had other plans down the line. So, armed with all this information, now we're going to go test this board. I don't have a Funhouse to test this board in, by the way, and honestly, I don't need a Funhouse to test this board. Knowing how this board works, we've gone through the basics of how this board works. All we really need in order to test this board is an input power supply, the ability to ground these pins, the enable and the driver up-down pins, and a load on the output of the board in order to see that it's working. And I don't have a 12 volt motor to use, but I don't need a 12 volt motor. I can actually use a 12 volt light, which you'll see in a second when we get this on the bench, that will serve just fine as a load and show whether or not this board is actually working. The last thing I did want to talk about, and I forgot to mention, is this resistor here. And this resistor in the circuit drops the output voltage to the motor. In NBA Fastbreak, they changed this resistor to a jumper, a through-hole jumper, or 0 ohm resistor, sometimes it's called that. That allows this voltage to be increased. So we're going to take a look at the impact that this has on the circuit and make a determination as to whether we want to keep this resistor in the circuit or we're going to do something else with it. So let's go to the bench. Okay, we're back and we're set up on the bench, and we have the board, the high driver board here set up, and what we have are the inputs. So this red pin here, pin 1, is 12 volts. Pin 2 is the black one, that's the ground. Then there's the key. Then this pin 2 is actually, this is pin 5, 4, 3 is the key. Pin 2, the red one, this is actually a jumper for the up-down for the motor. And what this does is it actually changes the polarity of the output to either plus voltage or minus voltage. And then the black one is the enable. So when this is connected to ground, it should enable the output. On the output side, we've got a white connector and a black connector, and the white connector is connected to the plus side of the meter as well as to the light bulb, the test light bulb here. And the black connector is connected to the minus side of the meter, and it's also, according to the schematic that we were looking at earlier, you've got your plus is pin 1, and you've got your minus is pin 3 on your motor. So that's how I have that connected. And we have this test light here. This is a 67 flash lamp out of a pinball game. This is actually a 12 volt light, which is perfect because we want a 12 volt load to test the output of this board and see that we want to light this up. And the way that we have this wired up is that we'll take a look on the meter once we fire this up to see what type of voltage we're getting at the bulb. So the other thing that we have is we have a benchtop power supply right there, and 3 guesses what the game is behind it. And this is a variable power supply that can go anywhere from 3 to 30 volts. Now, another interesting thing to note is that the 12 volt supply that powers this board in the game is the unregulated 12 volts. And that's important because you can have anywhere from 12, as the Williams manual says, you can have anywhere from 12 to 20 volts input into this board. Although honestly, if I was getting 20 volts input into this board, I'd be investigating why that were the case. Usually anywhere from like 12 to 14, maybe 15 volts at the most would seem the most logical voltages to get. So I'm going to turn this on, and you'll see that it comes up, and I've got just tweak it just a little bit just to get on the high side of 12 volts. So I got 12.1 volts that are now going into the board, and as you can see, the light is not on, and you can see I'm getting 15.4 millivolts on the multimeter, which is nothing, basically. It's virtually nothing. I mean, it might be warming up this element, but it certainly isn't going to drive a motor and isn't going to turn it. So now, if I take the black lead that's on pin 1 and I short it to pin 4, you'll see that the light turns on, and it shows that I'm getting 5.49. The number's actually going up a little bit. 5.5, 5.1, negative 5.5 volts going to this bulb, and it's still going up. And part of that is as the element warms up, it actually allows for a little more voltage to go through it. And you see the number continues to go up. So here we can see this board is actually functioning correctly. It's doing what it's supposed to do with the inputs, and then with the correct inputs you're getting your output on the board. If I disconnect the black lead, you'll see the light goes out, and then the voltage drops to near 0. And if I hook it up again, you'll see the light comes back on. Now if I take the red lead, which is hooked up to pin 2 over here, and I hook that to ground on pin 4, what'll happen is you'll see that I now have plus 5 volts, but I have less than the other voltage, and that's because the other pair of complementary transistors have taken over. So this is a situation where you can see that if the transistors aren't matched all the way around, that it can have an impact on the output of the motor. Now you can also see this sort of intensity of this light based upon the fact that we're getting about 5.6 volts. If I remove the red, you'll see we'll switch it over to the other 2, and now I see this is actually coming up to, or down to 5.6 volts. This is 5.66, 67, and as I toggle this back and forth, this would be simulating the difference between having the motor spin in one direction and having the motor spin in the other direction. And this is how this works in the game. You have an enable, and then you have the voltage changing direction, changing polarity, which changes the motor. Now what do we do about this voltage? We're getting about, now we're climbing up, we're at 5.7 volts. You know, this is probably going to keep going up. Maybe we'll get to 6 eventually. I think when I've tested this earlier, I got to maybe about 6 volts total at most. But that seems kind of low, especially for a 12 volt motor. How do I get this output to increase? Well, one of the things that Williams did was they got rid of this resistor here, like we said, and they just put a jumper in. We can simulate that by putting a jumper wire across the legs of this resistor. And electricity will always take the path of least resistance. So if I do this, then what will happen is the electricity won't go through the resistor, it'll bypass it, and it'll be just like I had a jumper installed. So if I hook this jumper up to the other side of this resistor, watch what happens to the light. You'll see that the brightness jumped dramatically. And if you take a look at the voltage, you'll see that we're now at over 8 volts coming out to the light instead of nearly the almost 6 volts that we had before then. So it's a significant increase in the output of this board. And if I hook up the red lead, and we want to see the positive voltage that can come out of this as well, you'll see that it's a little less, and obviously it sort of speaks to the pair that's on the positive side of this board. In fact, you see it's a whole volt less. So this can cause a problem with the motor, where if you don't have sort of matched pairs of transistors, you have this instance where you're straining the motor more in one direction than the other because of the fact that they're unbalanced. And you can see that the difference in the voltage, it's now 791 on the negative, 782, so they're getting close to the same here. And there's the negative again, and it's going back up. And if I remove this jumper, you'll see that the brightness of the lamp goes back down, and we're back down to like 5.75 volts. And we jump it, it goes back up over 8 volts. So what do we do now? Well, there's a couple of things that we can do. One of the things we can do, and one of the things I'm going to do, is I'm going to change out all of these transistors. And we're going to see what sort of effect it has on the output side of this board. I'm also going to change the LM339 as well. In fact, you probably noticed it's already socketed. It's not socketed from the factory. I did that previously just so that I'd be prepared to do this. And we'll see what a new LM339 will do, because these are also old and tired components. I mean, it's working, and you could, I could give this back to the guy who owns it and he can put it in the machine. The question is, what sort of strain is that going to put on the motor, and is this the optimal setup? So now what we're going to do is we're going to shut the camera off. I'm going to swap out a bunch of components, then we're going to come back and we're going to run these tests again, and we're going to see what it looks like. Okay, we're back, and I quickly swapped out all the Darlingtons on this board, the 3 tip 107s, 1, 2, 3, and then the 2 tip 102s. I also swapped out the 339 to see what impact, if any, that will have on the output. So now we're all set up again just like we were before, and I haven't even touched the power supply. It's still set for 12.1 volts, so I'm going to fire up the power supply and let's see what we get. So power supply is at 12.1 volts, and like before, we're going to take the black lead and we're going to ground it, and let's see what we get. So immediately we're at like 5.9, 6, 7, 8. It looks like we're going to get to about 6 volts here. Well, that's a lot more than what we had when we first fired up with the old Darlingtons and the old 339 on here. So certainly refreshing the parts is having an impact on the voltage. Let's see what happens when we go the other direction and we hook up the motor up down lead. And you see right there it's like 5.989, so it's 6 volts. So this is a worthwhile thing to do because it's matched basically the output on both sides of the board, the plus and minus outputs on both sides of the board, and we've gotten a little more voltage out of this, which is good, and that's what we wanted. The complaint from the owner was that the voltage going out to the motor was low. So now what happens if we do what we did earlier and we jump over the resistor to bypass it, just like if we were to put in the 0 ohm resistor here. And you see the light gets significantly brighter, and although it's probably blocking a little bit, and we're now at 8.4 volts. So this is a great voltage for the motor. In fact, probably like to even see a little more. So it kind of begs the question then, as I said earlier, this is powered by the unregulated 12 volts in the machine. And the chances of you actually getting 12.1 volts is pretty slim. It's probably going to be more like 13. So what happens if we go to the power supply and we bump it up from 12.1 volts to, let's say, 13 volts. Let's see what happens. So let's crank this up. And so now we're at 13.1 volts. And let's take a look at what we got here. Oh, that light's bright. Look at that. And look, we're at like 9.48 volts. So, wow, that's what you want to see coming out of this board if you have the motor hooked up. That's typically what you get, is about 9 volts. So what happens if we disconnect this jumper here and we go through the resistor? What sort of voltage are we going to get? Well, the light's less, but we're still getting over 7 volts now. With 13 volts coming into this board, we're getting 7 volts. So at this point, I think this board is good. I think the one thing I will probably do before I give it back to its owner is I'm going to remove this resistor and I'm going to put a jumper in here. And what that will do is it will ensure that the motor for Rudy's mouth is going to get the best voltage possible. Anything between 9 and 12 volts is ideal for that motor, and that's what we're looking for. So that would be the best result. And as you can see, I'll hook this back up again, and you know, we're at like 9.51, 9.52 volts. So you know, and I'm not worried about overvolting the motor. Like I said, the motor is a 12 volt motor. It's rated for 12 volts, and in fact usually you can go above that for most motors. So this is what we want. The other thing is that motors tend to operate more efficiently when they have more volts going to them. That's a general rule of electronics. So that's another thing that's we have going for us here. So this board is just about done. I'm going to swap that resistor, put it in a jumper, and then give it back, and hopefully the owner will be happy with it. So thanks for watching this video. If you like it, please hit the like button. Any comments, let me know down below. And thanks for watching. Okay, bye.